about remains from yesterday? Good. Just a short, some short words regarding what we did yesterday. Yesterday, we saw what happens when we have a solid, we have a crystal. When the first steps in quantum mechanics, when quantum mechanics was developed, was to solve how an atom, is what electrons, what the levels for electrons, something which could not be solved with classical mechanics. So quantum mechanics could solve that, and also could solve how a solid works. What are the electrons levels corresponding to a solid? And when you have a solid and you have that translation and symmetry, what appears is that the original levels that were for atoms, now they open and the energy bands appear, separated by bands which are not allowed for electrons. I'm talking with respect of energy. So they are pure bands in the solid. And those bands are going to control the electrical properties of the solid. We saw that essentially, if we have a monovalent atoms originally forming the crystal, every atom contributes with one electron. So every band has 2n levels available, where n is the number of atoms. In fact, I should say the number of primitive cells, the number of wells, that are formed when we put all the atoms together. So if you have a monovalent atom, you're going to have n electrons which are going to fill 50% of the band. And if that is the case, you're going to have a metal, because the Fermi level drops at a level where there are available states. So if you apply a field, an electrical field, an external electrical field, electrons can take another energies, change the number of electrons going to the right and to the left. Some unbalance can be created, and then we have a current. If we have 2 electrons per atom, we're going to have filled the first band. I'm insisting on these concepts because they are the things I want you to remain in your brains. We have a divalent atoms forming the crystal, then every atom is going to contribute with 2 electrons. You're going to have the first band completely filled, and a filled band cannot contribute to an electrical current, because we are always going to have 50% of the atoms going in one direction, the other 50% going in the other direction. So the total current is going to be 0. Going to atoms with 3 electrons each. Now we have going to have one band completely filled and the next one filled 50%. And that's we are going in a situation similar to a monovalent. We're going to have a partially filled band, and a partially filled band can contribute to electrical conductivity. Right. This analysis is done for a one-dimensional model. The model we saw in the case of the Kronig-Penney model. We see that in fact many solids formed by atoms which are divalent can conduct electricity. What is the answer for that? Well, the answer for that is that our model, one-dimensional model, does not apply in this case. There are new phenomena that take place in more than one dimension, and that is the overlapping of the bands. And if we have overlapping of the bands, we can have a large band formed by the sum in 2 bands, and in that case we're going to have levels, where the Fermi level drops, and that can conduct the electricity. Right? Okay. That was, in big words, what I want you to have in your minds after the first class. We're going to see some solid state physics today. I think that Most of you saw it, let's see, I guess in previous courses. And the question is, why atoms want to be together instead of being separated? And the reason eventually is energy, because being together we gain energy. The system gains energy. This can happen eventually because of electrical interactions. That is the origin of why molecules form and solids form too. Yeah, the interaction is electrical. We have not many interactions in nature. It could be gravitational, but gravity is not enough to have two atoms together. That is very low in interaction. The strength is very low. It's very small. Instead of that, well, the electrical interaction, yes, could have the right magnitude. It could be magnetic, but it doesn't work either. There could be nuclear forces, but nuclear forces are not involved in bonding. So the only interaction that can be responsible for that is an electrical interaction. Depending on how that electrical interaction acts, we can talk of different kind of bonding. Yeah, and this is what is said here. Let me see, like this. Yeah, the bond can be ionic, covalent, or due to van der Waals forces. Yeah, I guess you know about this. Van der Waals forces are very weak. They are related to dipoles that form, because atoms essentially are built of charges. We have a positive charge in the middle, and because of the nucleus and the electron, yeah, around. So if the nucleus is not exactly in the middle of where the center of the electron, yeah, the electron cloud around, we are going to have a dipole. So one atom can originate a dipole in the close atom, and then they attract each other, and that is called, these van der Waals forces are related to that. They're not very strong, but that is the reason why noble gases can make a solid at very low temperatures. You know that noble gases have their outer shells of electrons completely filled, so they don't make chemical bonding. It's not present. But anyway, at low temperatures they form solids. So the reason behind that, the van der Waals forces. Well, we don't care much about that, but for the sake of completeness, I'm talking about this. The typical bonding that chemists talk about regularly are the ionic bonding and the covalent bonding. In the ionic bonding, you have a transfer charge from one atom to another one. They form ions, and once you have positive and negative ions, they stick together because of electrostatic forces. This is how they explain to us how sodium chloride forms, for example. We have positive ions, yeah, the sodium, and negative ions, chlorine, and they form a structure which is an FCC. I think you know what that is. I'm going to remember that anyway. In the case of covalent bonding, that is responsible for the formation of a hydrogen molecule or an oxygen molecule. That is, molecules formed by two atoms which are the same. In that case, we don't have charge transfer, but essentially having two, yeah, we saw that having two nucleus, we can have two types of how the wave function can sum in two ways, yeah, summing up or one minus the other one. So we have two possible wave functions, and one of them, which is called the bonding, yeah, state, has a total energy which is lower. So in that way we can reduce the total energy of the system. Usually the potential between two atoms as a function of the distance decreases, yeah, and reaches a minimum and goes up. This is due to two types of interactions. One which is attractive, which is the kind of interaction we were talking. Yeah. For example, if we have an ionic bonding, the positive and the negative ions, the closer they are, the lower the energy. So we could suppose that at zero energy, at zero distance would be fantastic. But as soon as they are closer and closer, the ions, it appears a repulsive potential. Yeah? Because the nucleus starts seeing each other, and the clouds of electrons start to be smaller. They have to be smaller, and you know, in quantum mechanics, the distance, if electrons are confined to a small size, the energy goes up. So essentially, you're going to have a potential, yeah, repulsive potential energy, which is going to keep, yeah, the atoms separated. They don't collapse one against the other one because of the attractive, yeah, the attractive potential. To have a minimum, the shape of this has to be softer than the repulsive. So it has to go down first, the total potential has to go down first, and then it has to go up, yeah, because of the repulsive potential. It cannot be the other way, because in that case, in optics, we have the opposite form from the total potential, and things wouldn't work. Yeah? Okay. So, solids, you know what a solid is. Solids are resistant to changes in shape and volume, and solids can be, in general, can be classified as amorphous or crystalline. Crystals are solid that consist on a periodic arrangement of atoms, ions, or molecules, yeah, what we call translational symmetry. Typical crystals are diamond, quartz crystals, metals, ionic solids. Metals are crystalline, even at first glance. They don't look like, but in fact they are what we call, they are polycrystals. That is, they are formed not by the complete crystalline structure, which is ordered from the beginning to the end of the solid, but they are formed by small crystals that attach together, forming what is called a polycrystal. But metals have a crystalline structure. Ionic solids are like a salt, yeah, sodium chloride, diamonds, yeah, they're covalent bonding. And then we have amorphous solids, where that in which we don't have that order, yeah, that translational symmetry, not typical of glasses and plastics. Yeah? And in solids, we can have what keep the solid, the atoms together forming the solid, are the same interactions we saw for molecules. It can be the origin ionic, it can be of, yeah, covalent bonding, van der Waals forces, and now we have a new interaction which is called metallic. And in the metal, yeah, in metals, the total energy of the system is reduced because we are forming bands, yeah, and the valence band goes, yeah, spreads out. We have now in the metal levels which are lower than the original levels of the separated atoms. So electrons can accommodate in the lower part of the band, and that reduces the total energy. That is called the metallic origin, yeah, for the bonding in solids. Here we have a sketch to show what the crystal and amorphous solid are. On the left, yeah, we have a crystalline solid, where we saw a short range order. Atoms, every atom, for example, every red atom has 2 green atoms together, and the green atoms have 3 red atoms, yeah, close to them. And also there is a long range order. Yeah, you see it just by eye. It's intuitive. Instead of that, in amorphous solids, we can have a short range order. If you see, every red atom has 2 green atoms together, and every green atom has 3 red atoms, yeah, close to them. But there is no order in the long distances. Yeah. Good. Well, the periodic arrangement of atoms, ions, or molecules that form a solid or crystal is usually called a crystal or crystal structure. How that structure forms. I want to say something about this because many people describe things in a different way. Yeah? Chemists describe things in a different way that physicists do. It's very interesting. For physicists, I'm not originally a physicist, but I'm the club of fans of physics. So I'm inclined to their point of view. We have to make a crystal, we have first to describe the lattice. And the lattice is a periodic arrangement of points. So it's not something real. It's an abstraction. Yeah? There are points distributed in the space. So it's a mathematical abstraction. And the crystal is formed when we place atoms or a group of atoms, yeah, to in any place where a point is, yeah, in that lattice. So the crystal forms when we add a basis, that group of atoms. That group of atoms can be just a single atom. When we put that single atom or group of atoms related to any point in the lattice. And when we do that, we have the crystal. This is not an equation, mathematical equation, just a way of saying things. Yeah, the crystal forms when we sum a lattice and a basis. Many people describe things in different ways. Let's say I will show an example. Different solids can have the same geometry arrangement, yeah, of atoms. So they can share the same crystalline structure. And the solid that we have can have different properties because the basic atoms, yeah, that they're forming that solid are different atoms. But we can also have atoms of the same kind that are arranged in a different manner. Yeah, that is the case of carbon atoms that can form a diamond, a three-dimensional structure, or can form graphite, which is a layered structure. And as you know, diamonds have very different properties than graphite, even though they are formed at the same atoms. Graphite is what you have in pencils. It's not very expensive. Instead of that, diamonds are very expensive. You cannot convince your girlfriend that a piece of graphite has the same value as a piece of a diamond. Okay. Something that is regularly used to describe the crystals are the unit cells. The unit cell is a group of atoms that we take as a basis to, yeah, we put one unit cell close to the other one, and that way we build the crystal. These are the most very typical unit cells that you find in nature. BCC refers to body-centered cubic. I think you have seen this in material science. FCC is phase cubic center, and HCP is hexagonal, compact. These are the most typical unit cells in metals. Why metals like this type of structures? The reason is that these structures are quite compact. Yeah, are the more compact way of putting together spheres. In fact, FCC and HCP have the same occupation in volume. Yeah? And why metals like this kind of structures? Because metals like to have their atoms as close as possible together, because in that way we have more overlapping of the wave functions, and in that way the bands becomes wider, and as the band becomes wider, the electrons can go lower, and we gain energy. Yeah, that is not the case in covalent solids like silicon, for example. Yeah, in silicon, what reduces the energy is the covalent bonding, and the covalent bonding is very directional. So to gain energy, you have to have the silicons distributed in specific positions. So maximum density of atoms is not what the silicon atoms look for. Yeah? Good. These are called unit cells, but I want to tell you something which creates confusion. In fact, strictly speaking, we should talk of primitive cells. Have you seen the things? A primitive cell is a smaller, cell, which by reproducing them, we build the crystal. For example, in a cubic cell, in a simple cubic, which is like the BCC without these atoms, we have atoms just in the corners of a cube. The unit cell is similar to the primitive cell. This is the smallest cell we can define to build the crystal. That's the primitive cell. And why don't we do the same with the FCC, for example? Well, the problem with the FCC, that primitive cell, is very complicated. No one understands what's going on if I show you the primitive cell corresponding to the FCC. It's a weird shape there with connecting some atoms, and it's very complicated to see it. So instead of that, people define unit cells. Cells or conventional cells are also that name is used. Conventional cells. That unit cell we have here is a conventional cell, which is much easier to describe. This is a cube with atoms in the corners and the center of the faces of the cube, and everybody understands that. Instead of that, the real primitive cell corresponding to FCC is very difficult to see in space. But I want you to know that because people get confused with that regularly. Okay, here we have the structure of diamond. Diamond have an hybridization. That's the way of saying hybridization sp3. So every atom has 4 bonds, which are directional. In such a way that if we have an atom in the center, if we draw a cube, the atoms which are in these 4 corners are going to be bound to that central atom. And then the unit cell is that weird structure we see here, which in fact is an FCC. And this is another problem. I mentioned that people describe the things in 2 different ways. Physicists, but of course we do it well, describe the things considering that this, you see the white, all the atoms here are the same, but none are white and none are gray, but they are all silicon atoms. But essentially, if you see that, if we see here we have atoms in the corners, and here we have atoms in the center of the faces. And furthermore, we have another atoms which are this in the middle of the cube. If we don't consider those, the rest of the atoms are going to form an FCC. So the correct way to describe this, that is, there is no manner to describe this with a lattice, putting points on where every silicon atom is. There's no way of doing it. So the only way to describe this is having as defining the basis of 2 atoms, for example, this and these 2 together, and putting to every place where we have a point corresponding to an FCC a couple of atoms that is the basis of 2 atoms. Well, this can be described too, and chemists do it in this way, saying that we can have an FCC structure of silicon and another FCC structure of silicon. And we put one inside the other one with a separation of 1/4, 1/4, 1/4. And we reproduce, similarly we can reproduce the silicon structure. But that's the way chemists do it. We prefer to describe first the lattice with the points, and to every point assign a couple of atoms, which is the basis. Oh no, we have physicists here and chemists. What are physicists? You're chemists? Physicists, everybody physicists. I don't know. You are not used to that? Ah, you're used to that. You prefer that, this kind of description? Both. Okay. It's a lot of discussion of that. It's amazing, and it's I didn't know if that was just something that happens in Argentina, or, yeah, or it's a global problem. Yeah. Yeah. Good. Okay. After this general introduction in solid state, we go back to metals and insulators. We saw yesterday then the band which is filled in half corresponds to a metal, and insulator has a completely full band, which is called the valence band, because they are at 0 Kelvin. We have all the electrons, yeah, corresponding to the valence electrons, the last shells in the atom. Yeah, and the next band is at 0 Kelvin is completely empty, and we call it the conduction band. Yeah. So we go back to this structure, and in particular for semiconductors, the gap between the conduction band and the valence band is not huge, in such a way that at room temperature we have some electrons here in the conduction band and some electrons in the valence band. So this case is what we describe as a semiconductor. Semiconductor is similar to an insulator, with the difference that the gap is not so huge. So we have carriers. What we are describing is an ideal semiconductor, or also called intrinsic semiconductor, where it's just perfect. We don't have any kind of defects, any kind of extra atoms, just the atoms forming that form the crystal. That's it. So how electrons occupy those states in the whole solid? Well, at 0 Kelvin, yeah, the Fermi function could be just a step function. The conduction band will be completely empty, and the valence band completely filled. But as temperature rises, the Fermi-Dirac function changes its shapes, and now at the bottom of the conduction band, the probability of occupation of those states is not zero. It has a value. Yeah. So that is meaning that we have some electrons here. Where do those electrons come from? Well, they come from the valence band, which now the probability of having an empty state here, yeah, is non-zero. That would be 1 minus f. Yeah, the probability of having an empty level. So here we have the Fermi level. Then these are the density of states, and the bottom, yeah, of the conduction of the band, and the top of the band, the density has a parabolic shape. This is easy to see because we're in a minimum. In the minimum, we have a level. The first derivative is 0, and then we describe this with a Taylor expansion, and the first relevant term is the quadratic term, so it has a quadratic form. So here we have some electrons, and here we don't have electrons that were before at 0 Kelvin. So if we multiply the probability of occupation times the density of states, we are going to have the density of electrons. So the product of this times this is going to be something like this. Yeah, the product of the Fermi function times the density of states. And in the other way, here we're describing the density of empty states. That's why we have 1 minus the Fermi-Dirac function times the density of states. And we have something which is essentially quite similar to what's going on here in the conduction band. Yeah, we have a mirror here. It's quite similar. It's not exactly the same. Why is not exactly the same? The Fermi-Dirac essentially has some point of symmetry here. And who is responsible for not exact symmetry of this density of states and in fact it's the density of the states here which are not exactly symmetric. Yeah, bands are not exactly the same. So essentially, if we want to know how many electrons we have here yeah, in the conduction band, how many of these states are occupied, we have to integrate the product of these two things. Yeah, so we want to know the area of this curve, and it's very difficult to do. You have to, I guess you have done it in some courses. There are some simplifications which are recommendable to do. That is to consider the Fermi-Dirac function is just like a Boltzmann exponential decreasing function, because the Fermi level is far away. Yeah, and 1 minus f also gives an exponential that decreases in this direction. And we take the density of states of the parabolic form, and we can integrate that. And after the integration, you get how many electrons are in the conduction band and how many empty states are in the conduction band. Those empty states are called holes. Yeah? And amazingly, these holes behave as carriers. For electricity, they behave as carriers. Yeah? The electrons, you understand. You have electrons in the conduction band, you apply a field, the electrons move following the field. And we have holes. How does it work? There was a game when I was a child, very popular, called 15. I don't know if you have it. It's just in a square made and have 4 times 4 with 14 small squares. Yeah, sorry, times 4 and 16 squares, but there were only 15 small squares. It was an empty square. And they have numbers, and you have, can you move the smaller squares and put an order there? You have that? That was very popular in my time. It's called 15. Okay, when you move the small squares, yeah, that's the real thing, the squares which are there. But essentially what you saw is the empty square moving. Yeah? That empty square moving, in fact, is not real. What is real are the 15 real squares. But you can describe what's going on in that game looking at how that empty square moves. Yeah? And that square, that reminds me of the holes in a semiconductor. That is, most of the sites are occupied, but those sites which are not occupied are the holes. And it was very interesting. Those holes behave as carriers, and behave as carriers of positive charge. Yeah? Okay. Here we have some detail on how to obtain those formulas. Okay, we want to know how many electrons per unit volume we have. We have to integrate the density of states and the probability those states are occupied. And we have to integrate from the bottom of the conduction band, which is EC, to the maximum of that band, and which we put in maximum. Anyway, we don't care much what's going on with the density of the states, just at some tens of electron volts far away from the bottom of the conduction band, because after that, the Fermi-Dirac function, which is an exponential decreasing, is going to make the integrand quite negligible. Yeah. So what we can do to simplify things, instead of putting here the maximum, we put infinite. Yeah. It's not going to change results much, because the integrand is going to be very rapid. It's going to go to 0. Yeah, to values of a minus af larger than 3 kt. The exponential becomes very small. And we are going to take the density of states. The density of states we found for the box. Yeah? And it had that shape. It was a parabolic form. The only thing which is slightly different is the mass here. In the box we have the regular mass of the electron, and here we have what is called the effective mass, at the end with an asterisk. And the reason for that is that the density of states can have a shape which is not exactly what we expect for a free electron model we made. Yeah, and essentially that exponential, that effective mass depends on the curvature of the density of states. Well, here we have to make this product, but if we take this one, it's very difficult to integrate. But since E minus F over KT is larger, this exponential is quite large, we can get rid of the 1, and this becomes a Boltzmann distribution, just an exponential. So we can make the integral, and the integral ends up with this form, which is not very difficult. We have some NC, which is a constant, which is regularly known as the effective density of a state, and an exponential. As far as the Fermi level is deep in the EC minus EF is larger, so the Fermi level is deeper in the gap. The number of electrons decreases. As this difference is smaller, the Fermi level goes up, the number of electrons increases exponentially. Which we wouldn't expect, because as the Fermi function gets into the conduction band. And in a similar way, integrating the empty states in this case and the G of E in the valence band, we can find how much the density of holes is in the valence band. And it's quite symmetric. That is, as soon as the Fermi level goes down, the tail of the Fermi-Dirac function gets into the valence band, and more sites are empty. And this effective density of the states is related to this constant in this way. And here we have the effective mass of holes. You remember the effective mass depended on the second derivative of the dispersion relationship. And so if these effective masses are not the same, these constants are not exactly the same. If the effective masses are the same, the values of NC and NV are the same. In that case, what do we expect? Suppose NC is equal to NV. What do we expect the Fermi level is going to be? Well, in that case, we have some symmetry. What I want to say. If this is exactly the same than this, since we have a symmetry point here for a Fermi-Dirac function, to have the same, we have to have the same number of electrons, the same than holes, because at 0 Kelvin we have none of them. As soon as we raise the temperature, some electrons jump from the valence band to the conduction band. So every time we have an electron, we also have a hole. With what we have seen so far, that's the case. So the number of electrons have to be the same as the number of holes. If NC is equal to NV, we have some kind of symmetry. You see? For N to be equal to P, we need this exponential. If NV is equal to NC, this exponential has to be equal to this exponential. So if EC minus EF is equal to EF minus AV, that means that the Fermi level has to be exactly in the middle of the gap. You follow me? But that is not the case if this NC is different than NV. And NC and NV, the only thing that can make them different is the effective mass. And the effective mass is related to how this G of E, the shape of this G of E. So if NC and NV are not exactly the same, the Fermi level is not going to be exactly in the middle. But just a small correction makes it. Why? Because this is an exponential, so a small change in the Fermi level changes this exponential a lot. So in principle, we can say that in this case we are dealing with, which is an intrinsic semiconductor. Intrinsic for pure has nothing. Then we are going to see how things can change. But so far, this is an intrinsic or pure semiconductor. If the Fermi level drops about the middle of the gap, right? Because we need to have the same number of electrons and holes. yeah, to have a neutral semiconductor. Okay, so we can write down things and more mathematically and say saying if n is equal to p, I think you have done it. Yeah, we can, from this equating n and p, we can extract how much the Fermi level is, and it has this shape, this form. Yeah, and see that here we have the ratio between the effective masses. If the effective masses are the same, that is telling us the density of the states are the same. And the logarithm of 1 is 0, so this term wouldn't be here, and the Fermi level would be exactly in the center of the gap. Dc minus dv over 2. Yeah? If that is not the case, the effective masses are not exactly the same, we will have a small correction. See, we have here 3/4 of kT, unless it is a terribly huge number, which regularly that's not the case, we're going to have a correction in the order of kT, which is supposed not to be a big number related to the gap. Yeah? If the effective mass for holes is larger than for electrons, what does it mean? That the curvature of the valence band is larger than that of the electron. The other way around, this is smaller. Yeah? It used to be flatter. Yeah? The effective mass depends on the inverse of the second derivative. If that is the case, it means that this G of E is something like this, with a curvature, yeah, and smaller curvature. If that is the case, the density of a state here is going to be larger than here. So to equilibrate things and to having the same number of electrons than holes, the Fermi level has to go to the right. Did you follow me? Yes. No. Good. I just wanted to see things intuitively, yeah, from looking at because this is a mathematical, yeah, function, but where is it coming from? What is telling us? Yeah, why, if you have an effective mass for holes larger than for electrons, the Fermi level goes up? Goes up because if it stays in the center, I'm going to have more holes than electrons. If you want the number of electrons to be the same as the number of holes, the formula has to go a little up to correct for the different density of states in the valence band and the conduction band. Okay? Well, so far we have been dealing with intrinsic semiconductors. Yeah? So for an intrinsic semiconductor, we apply the field. Here, put it from right to left. Electrons in the conduction band are going to move to the right. Yeah? And holes are going to move to the left, following the electric field. Both are going to contribute to the conductivity, to the current, to the total current. Here we have the both density of holes and electrons. This is the gap. And this is the way an intrinsic semiconductor would conduct electricity. Yeah. Something interesting I didn't mention. During years before quantum mechanics, people did not understand why there were materials that, when increasing the temperature, the conductivity decreases, and there were other kind of materials that, when you increase the temperature, the conductivity increases. Yeah? In metals, when you increase the temperature, the resistivity increases, and the reason for that is that the mean free path for carriers is reduced because we have more interaction with phonons in the structure. Instead of that, in insulators and semiconductors, when you increase the temperature, yeah, the number of holes and electrons increase exponentially. Yeah, and we saw as more of this is, yeah, since here we have the Fermi-Dirac function, the tail on one side and the other one gets into the conduction imbalance band, and we are going to have more carriers. So in metals, the conductivity decreases with temperature because the mobility of the carriers is reduced. The same happens in insulators and semiconductors, but simultaneously the number of carriers increases exponentially, and that is dominant. Yeah? And that's the way insulators die. You know that they die very fast. What is this guy saying? What I want to say is the following. Suppose the temperature increases, and the insulator is a very old insulator having some cracks and things like that, so it starts conducting a little more. Yeah? Well, it doesn't matter, it's still a good insulator, nothing happens. But the insulator is suffering more voltage and stress, and then the conductivity increases a little. So we are going to have a leak current, which is increasing as the insulator becomes older, yeah, up to a point in which the current, this leak current, is enough to heat up the insulator. If the insulator gets more temperature now, we are going to have more carriers, and if we have more carriers, the heating is going to be higher because of the Joule effect. And if the temperature is higher, we are going to have more carriers, and more carriers, more heat, and more heat, more carriers. This is a positive feedback. The insulator dies very fast. Yeah. Okay. Well, we're going to jump to extrinsic semiconductors. We talk about intrinsic semiconductors because it's a pure semiconductor. It's a way to start with, an ideal semiconductor. But in fact, when you made a semiconductor, it's very difficult not to have defects. Yeah. So in fact, what we have just seen is an idealization. That is, we are not going to have in real life an intrinsic semiconductor. Naturally, it has going to have defects, and those defects, you don't need many defects to make them responsible for the conductivity in the semiconductor. Yeah. After all we have talked, I'm telling you that kind of semiconductors do not exist. It's terrible. Yeah, I know, but if I started saying that, you wouldn't have paid much attention to me. But this is the starting point to have an extrinsic semiconductor, the real semiconductors. In electronics, yeah, in the electronic industry, people can make with typical semiconductors like silicon or gallium arsenide or germanium originally, you can decide what type of defects we can have in the structure, what type and in what density. Yeah, that is typical in the electronic industry. So you are going to decide, okay, I'm putting here silicon because 99% of the electronic industry uses silicon as the basic semiconductor. Yeah, and you can choose the doping. I'm mentioning this because in this kind of semiconductors that we are going to talk later, in oxides, that is something you do not know, and it's a nightmare because you don't know what is going to happen in an oxide. But let's leave that for later. So in the electronic industry, say in silicon, you can put into the structure some defects, which are other kind of atoms. And the trick is the following. The typical dopants are those I draw here, this phosphorus and this boron. And what happens here? Well, the phosphorus have 5 valence electrons, and silicon had 4. So I'm very old man. I remember games when I was a kid. Have you played to that game of the chairs? There are less number of chairs and people, and one at the end cannot have a chair. Well, this is the same. Here we have 5 electrons, but there are 4 chairs. Yeah, these are the directional bonding to silicon, to the 4 neighbors, 4 silicon neighbors, and the phosphorus energetically is comfortable occupying the site of a silicon. He wanted to be a silicon, so takes the place of a silicon in the structure. Something which is nature has been helping us is that in the structure of the silicon, yeah, and the crystal structure, every atom has 4 neighbors. So it's very easy to describe things in in a two-dimensional structure like this. Of course, this is not the real structure, it's sodium and silicon. But since we have four atoms, each atom has 4 atoms, neighbor atoms, we can draw things in a quadratic a crystal. That is not real, but it is good to describe it, because usually blackboards and drawings we make, we use a two-dimensional blackboard. So it's easy to understand things in 2 dimensions. So the phosphorus takes, I was saying, a place of a silicon, and 4 of the atoms contribute to the bonding with 4 silicon neighbors. But the 5th electron doesn't have a chair. Where can I go? Says the electron. So the electron, this remaining electron, everything what it sees is a phosphorus, which is an ion. It's positively charged, right? Because it would be neutral, you have the 5 valence electrons, but you have 4, so it's positively charged. So this electron sees that ion there in the middle of the structure, which is positive, and this looks like a hydrogen atom. This will have a positive charge and an electron. This is what it sees. So these electrons, in principle, start moving around this, this positive charge, like in a hydrogen atom. But this is not exactly a hydrogen atom. Why? Because this electron is moving in a medium which is not vacuum. This is silicon crystal. And the silicon crystal, the electron can have a different effective mass, not the mass of a free electron. And more important than that is that the electron is moving in a medium with a permittivity which is much higher than that of vacuum. Because of that, the first level, corresponding to a hydrogen atom with those characteristics, the energy is very small. It's very small. And since it's very small, very easily at room temperature, this electron leaves his parent atom, goes to the conduction band, and becomes a free electron in the conduction band. So after doing this, we impurify the silicon with this phosphor, which has 5 valence electrons. We're going to end up with a crystal, with a semiconductor, which has more electrons than holes. So for that reason, this type of semiconductor is called an N-type semiconductor. N for electron, because it has negative, the carriers are negative, are electrons. All the way around, there is a way of saying this in Latin, mutatis mutandis. Have you heard that? Mutatis mutandis is changing what has to be changed. If instead of having an atom with 5 valence electrons, if we purify with an atom having 3 valence electrons, like boron, now we have more chairs than people. Well, in this case, more chairs than electrons. So the boron also is a substitution. It's called a substitutional impurity in the structure, because it substitutes an original silicon, which should be there if the crystal were perfect. Okay, that boron has 3 valence electrons. You can satisfy three bonds, and the 4th bond, we don't have electrons. So, but since this is just one atom in a sea of silicons, very easily one of these electrons jump in here, and that makes this boron a negative impurity in the structure. And that hole that is here easily jumps to other silicons. In fact, it's not the hole. There are other silicons that are jumping there, like the 15 game. But we can see, instead of dealing with millions of electrons, we deal with that specific hole. It's easier to see how the hole moves that the whole number of electrons do. Well, this is what regularly we have, extrinsic semiconductors. This is real life. And as I said, in electronics, you can choose. what kind of what level of doping you have in your semiconductor. Well, and what happens with the Fermi level and electrons and holes in these extrinsic semiconductors? As I said, for if we are talking of this kind of dopant, as phosphorus, we say that this dopant is a donor because it donates an electron to the structure. Yeah. So if we have donors present, we are going to have an N-type semiconductor, and this is what I was talking about, an hydrogenic atom. This is the energy for an hydrogenic atom. Originally, if the mass is the mass of a free electron and the relative permittivity is 1 of vacuum, this gives you minus 13.6 electron volts, which is huge. Yeah. But for example, in silicon, the permittivity is in the order of 13, so we have 13 to the square, which is almost 200, and this ratio also is smaller than 1. So eventually the energy, the first level of this hydrogenic atom is quite low. Well, how we can calculate the density of donors which are occupied? Well, the level of these donors is very close to the conduction band. Is it here? If the Fermi level were here, all this level would be empty. Yeah, because the distance will be very. Yeah? So the donor, how many of those donors are occupied? Well, that is related where the Fermi level is and where the donor level is. So we can apply the Fermi-Dirac probability for them to be occupied, which is 1 over the exponential of the donor level minus the Fermi level. Yeah. So this is going to give us the density of donors which are going to be occupied. But what we really care about is about the number of donors we are going to be unoccupied. Because those which are unoccupied and become positive ions means that at the same time we have an electron in the conduction band. We want to know how many electrons we have in the conduction band. So the numbers we want to do is to know from the total number of the density of donors, how many, the difference of the total minus the occupied, are going to give us the number of unoccupied donors. And it's very interesting because if you can make the numbers, you make the calculation, you have only to change these two. Yeah? Have you done it? Yes? No? Once in your life, have you done it? Do it. Make these differences. ND minus this. You have to have a common denominator and make the numbers, and you're right to this. Well, this was for an N-type semiconductor. For a P-type semiconductor, we want to know how many of those levels are ionized. If they have an electron, that means that we have a hole in the valence band. Yes. So here you don't need to make any calculation. This is the total number of ionized acceptor levels. It's called acceptor levels because they accept an electron. Yeah. Takes the form essentially the total number times the probability of occupancy, which is just a Fermi-Dirac function. Okay. So eventually, for an N-type semiconductor, see, we have a donor level in here, and since these donor levels, for example, originating in phosphorus and silicon, donates electrons to the conduction band, somehow we are going to have more electrons in the conduction band than holes in the valence band. And if that is the case, what is the parameter which is adjusting this? The answer is the Fermi level. the Fermi level has to be different. That is, the Fermi level originally was here about in the middle of the gap. We saw the effective masses were the same, it was exactly in the middle of the gap, but now that is not the case. So to have more electrons and holes, we need the Fermi level to go up. So in this case, the Fermi level is going to be above the middle of the gap, and we're going to have an N-type semiconductor. Okay, so this is somehow a picture of what was going on, on all I was telling you, I was commenting to you. Originally, we have an intrinsic semiconductor. I know it's an abstraction, but let's suppose we have an intrinsic semiconductor. The Fermi level was about in the middle of the gap, yeah, and we have the same number. Look at the. I did this by hand by myself, yeah. So the number of holes and electrons that are here are not just any number, yeah. Here we have the same number of holes than electrons, 4 and 4. Well, it was not so difficult. We have to count up to 4. I know I chose a simple problem. Yes, and this position of Fermi level is called the Fermi level position for an intrinsic semiconductor. That's why it's called EFI. Yeah, EFI. For the case of an N-type, the Fermi level is not in the middle of the gap. It's higher, as seen here, because with the Fermi level for an N-type semiconductor, the number of electrons now is more, and the number of holes is lower than before, right? Because the distance between the Fermi level and the EV is larger, so the number of holes reduces. So as the number of holes increases, the number of electrons, the number of, did I say it well? As the number of electrons increases in the conduction band, the number of holes in the valence band reduces. The other way around, for a p-type semiconductor, yeah, we have those boron, which are acceptors. So we increase the number of holes. The Fermi level has to go down now to have this number of holes. But simultaneously, when the Fermi level goes down, the number of electrons reduces. You cannot increase both simultaneously. You see the problem? What happens if I impurify the semiconductor with boron and phosphorus simultaneously at the same time? Am I going to have more electrons and more holes? No. There is no way of doing it, because the Fermi level is going to change, yeah, depending on if you put more dopants than acceptors or the other way around. But the Fermi level is 1. Once you have a Fermi level, you have a specific number of electrons and a specific number of holes. Yeah, but the Fermi level for the whole system is the same. So it can go up or down. Yeah? And if it goes up, you're going to have more electrons and less number of holes, and the other way around. And something interesting, the product of the number of holes times the number of electrons is constant. So as one increases, the other reduces proportionally in the same way, such as the product is the same. That is what I was telling you. Here I have 4 and 4, the product is 16, and here I put 8 electrons and I put 2 holes, so the product is also 16. Because I'm not putting something just by chance. Yeah, the product has to be constant. There are different manners to understand that. When I wasn't a student, they just told me, hey, look at the equations, and that's it. Here they are. No. Where are the equations? Here. If you make the product of n times p, yeah, makes n times p, I'm going to see here that EF it has minus is plus. So the density of electrons depends exponentially on the Fermi level. The larger the higher the Fermi level, exponentially we have more electrons. And here P, because the Fermi level has a minus sign. When you make the product, the Fermi level disappears. So the product is independent of the Fermi level position, right? And it's going to give you a number that depends on NC and V, and on the gap. We're going to have minus EC minus EV. over kT, right? And the product is constant. Yeah, it's constant in the sense it's independent of the Fermi level, but obviously it depends on the temperature, because the temperature is here, and then C and at V, here's the 3/2, is going to change, but not much compared to this exponential. As the temperature increases, the resulting exponential is going to be, the exponent is going to be smaller, negative is smaller, so the product is going to increase a lot as temperature increases. But for a constant temperature, the product is constant, in the sense that it's independent of the Fermi level position. Well, we were here. Well, that's the way mathematically to show that the product n times p is constant. And since it is constant, I can say that n times p is equal to ni times pi, where ni is the density of electrons for the intrinsic semiconductor, and p is the density of holes for the intrinsic semiconductor. But the density of electrons and holes in an intrinsic semiconductor were the same. So that's why I can write the density of electrons to the square. Yeah, it could be also pi squared, or ni times pi. Yeah, but it's constant. This thing is called the mass action law, the law of mass action in semiconductors. Have you heard of the law of mass action? Yeah, in reactions, chemists love the mass action law. Have you heard that? Yeah. This is applied to in electronics, but this comes from chemists. You see, I like some things coming from chemists after all. Well, what is the reason for this? Having you apply the mass action law, for example, you have a reactive times another reactive, you have the compound. Now the ratio between the densities of this divided the ratio of this gives you a constant. Have you done that? Depending on the stoichiometric factors, so the stoichiometric factors goes an exponent. Yes. The chemist explained that to me. Well, here is the same. That is the reason that is when the phenomenon that an electron goes from the valence band to the conduction band, generating a hole and an electron, there's some kind of reaction that you need an activation energy. You have an activation energy which is the gap. As an electron have to jump from here to there, as in a reaction, yeah, a chemical reaction. And in equilibrium, we have what is called a recombination. That is, the electron finds a hole, yeah, goes to the hole, and both disappear, yeah. So, when we are in equilibrium, the rate of creation of electron-hole pairs, we say that because once you create a hole, you're creating an electron. The conduction band has to be the same as the rate of recombination, and that's the equilibrium situation. Okay, so we have some kind of like a chemical reaction, which from nothing, because well, nothing, from this sea of electrons at the sea of empty states, we generate an electron and a hole. So from nothing, electron plus hole. Now we apply the law of mass action. How do you say, the law of mass action or the mass action law? The same. You understand both ways? I don't know what is correct. The law of mass action. Thank you. The law of mass action. So we have on the right the two products of the reaction, which are an electron and hole. So we have to put the density of these things, which is n times p, and that has to be equal to what we have on the left. On the left we have this sea of electrons which are here, but since we are taking just a few amount of these electrons from there, the density of these guys is practically constant. So you can write n times p is equal to a constant, which is what is written here. So that's the reason you're going to find this as in the literature named as the law of mass action, coming from a chemical reaction. Yeah? I want you to remember this because we want to talk about this later when we were talking about about the gas sensors. I'm going to talk about this afternoon too. Okay, so I have to do this. Mouse escape. I have to touch the full screen. This was with this, yeah. No. Also, escape again. View. Full screen. Good. Good. Wow. I got a 9. A B. Okay. Well, so we are talking now about extrinsic semiconductors. Extrinsic semiconductor. If we are in the bulk of the semiconductor has to be neutral from an electrical point of view. So the total number of positive charge, the total density of positive charge, has to be equal to the total density of negative charge. So if the crystal is neutral, the sum of the let me see. This works, not like this. Now what do I have to do? Yeah. Well, that small thing is going to remain there. Okay. The total positive charge we have in this semiconductor is, we have two types of positive charges. We can have donors which are ionized. Those positive charges are charges which are fixed in the crystal structure, plus the holes which are moving around. They are the carriers, positive carriers. And the other way, we can have negative charge. We can have electrons, yeah, which are carriers, and acceptor levels, which are fixed in the structure, which are the dopants we put into the structure. And this is a general equation we have to satisfy if the crystal is neutral. Well, what is the only parameter we have to make that the positive charge, the density of positive charge is equal to the density of negative charge? Well, the only adjustable parameter we have is the Fermi level. So the Fermi level is determined by this condition. In the case of N semiconductors, the Fermi level is going to be close to the bottom of the conduction band. And in the case of p-type semiconductors, the Fermi level is going to be close to the valence band. However, always this condition is satisfied. We saw the product of P times N, that is the density of holes and electrons, is constant. Typically, people working in electronics deal with N-type or P-type semiconductors, and they dope the crystal with one or the other of the dopants. For example, if we have an N-type semiconductor, well, to have an N-type semiconductor, we need Nd to be much larger than Ni. That the dopant density I used has to be much larger than the intrinsic density of electrons. If not were the case, we were having just almost an intrinsic semiconductor. So suppose you want to have an N-type semiconductor, Nd, the density of dopants, has to be much larger than the density of intrinsic electrons. If that is the case, practically all the dopants are going to be ionized. If the density is not very high, the Fermi level is going to be up, but the distance between ED and EF is going to be larger than 3 kT. So most of them are going to be ionized. So the density of electrons, how much is going to be? Well, it's going to be equal to the density of dopants I put. So I control, in electronics, people control the density of carriers. And what's going to be the density of holes? Well, it's going to be much lower than before, before impurifying the semiconductor. And using the result of the mass action law, we say that P is going to be Ni2 squared divided Nd. Because Nd is N, and if I go in that direction, then P will be, well, Ni2 squared. And see, if we do this, N times P, we get Ni2 squared. Well, in general, semiconductors have holes and electrons. Oh, I wrote electrons in Spanish, sorry. I realize now. Electrones, we say. We have holes and electrons that contribute to their conductivity. Well, if we define the mobility, mu as the mobility relates the speed of the carrier related to the applied field. And the mobility is related to the time between collisions of the electrons. So the speed is going to be related to that time. The longer the time before collisions, the electrons have more time to accelerate due to the electric field. So the speed is going to be larger. So it can be easily deduced that the mobility, which is the velocity divided the field, it has this form. That is, the mobility is going to be larger as the larger is the charge of the carrier. So the force is going to be larger. The larger the time between collisions, because they have to start accelerating again. And inversely related to the mass. The larger the mass, the acceleration is going to be lower. So finally, we can write things, as shown here. We have two kinds of carriers. We are going to have this is the Ohm's law, the current related to the field is proportional, and the proportionality is the conductivity sigma here, which makes sense. That as the conductivity increases, let's think we have only one type of carrier. The conductivity is going to be proportional to the density of carriers, the charge of the carriers, and the mobility, which makes sense. Since they move easily, the conductivity is going to increase. If the charge they transport, the conductivity will be larger. The larger the number of carriers, the larger the conductivity. This is very general. Usually we have one of these terms. If it is n-type, you're going to have only this term, and if it's p-type, you're going to have this term. They're going to be the dominant. Well, just to know a little about what's going on in this dynamic process. As I told you, the generation and recombination of electron holes are the key to the dynamic process, which we can describe in equilibrium with the Fermi-Dirac function. Amazingly, the Fermi-Dirac function describes things just in one shot. But in fact, what's going on dynamically is a creation and a generation and recombination. So semiconductor carriers are created. Here typically said that they are generated, and they are eliminated by recombination. See? Generation corresponds to the transition of an electron from valence band to the conduction band, and recombination is the reverse transition. Well, under equilibrium, both processes have to be balanced. This is the number of electron holes I'm creating have to be the same as the number they are, they're recombined. Heuristically, I like that term. That comes from Latin. You know what heuristically means? No? I would say good sense. It's something we can say without demonstration. See, the recombination. Thinking we have you play billiard, you say, with spheres that knock each other on the table. That's called billiard. Good. Well, if you imagine white and black billiard balls bouncing on the table. Once in a while, one black ball knocks against the black one. Every time that happens, you take out both from the table. Well, that is some kind of picture you can have of how the recombination takes place. Well, how many recombinations per time you're going to have? Well, the more balls I have, the more recombinations are going to be, because most likely they knock one to each other. If we double, suppose you have 10 and 10 billiard balls bouncing. Yeah, and now we increase the number of, say, of white balls. What's going to be the number of knocking one to each other per time? It's going to double. Do you think it's intuitive then? Okay, if we double the number of white balls, the number of collisions per unit time is going to be doubled too. And if we double the number of black balls, well, it's the same. It's going to be double the number. So you can easily think that the number of times an electron and holes are going to find each other is proportional to the number, to the density of electrons and to the density of holes. Yeah, that's what we call heuristically. We can accept that it's correct. So in equilibrium, the generation must balance recombination. So let's say that at a specific temperature, the generation is this G0, yeah, generation. So in equilibrium, the recombination, which is proportional to the densities of the N0 and P0, which are the densities of electrons and holes in equilibrium, has to be equal to the generation of those, yeah, pairs. Recombination has to be equal to generation. Well, suppose that the population of electrons becomes unbalanced. How that can be unbalanced? And because you shoot it with a laser, for example, light your semiconductor. You produce a lot of hole pairs which are above the equilibrium. Yeah. Well, somehow the system has to recover itself and find its equilibrium situation. Well, let's suppose we have extra number of holes and extra number of electrons due to that light. Well, if that happens, we can bend the what is going to happen? Now we're going to have more electrons and holes than in equilibrium. So what is going to happen? The generation is going to be the same because it's a thermal process. But the recombination is going to be larger because we have more than in equilibrium. You understand? Okay. So the difference between generation and recombination, that is not going to be the same. Now we have to have more recombination. Well, we can write this in this way, and we can replace N and P for the row here. Yeah, and you can do it. This is not very difficult. You have to make the product of all these guys, yeah, together. If you do that, this R times P0 times N0 disappears because G0 is that. Yeah, and then you have a lot of combination, which is going to give you a nonlinear equation. It's not easy to solve. However, for an extrinsic semiconductor, it's not difficult to do it. Why? Because in that case, N is much larger than P, so some terms can be ignored, and eventually you arrive to a differential equation. This is how N and P changes with time, and you can easily write things this way. This is telling us that at larger times, this thing disappears, and we go to the equilibrium for the density of holes. But essentially, this is the initial density of holes. Yeah. The extra density of holes we have with respect of equilibrium, which will be the number of holes at time 0 minus the density of holes in equilibrium. And they're going to disappear in an exponential way. And this 1 over R and O could be the time constant for them. Right? So if you are working with light and semiconductors, you increase the number of carriers, they are going to disappear when you stop illuminating the sample in an exponential way, because usually semiconductors are extrinsic, so the density of carriers are going to decrease exponentially, and the constant time for that depends on the speed, this R, which is related to the recombination speed, times and zero. That is for P. This is for an N-type semiconductor. So the larger the density of electrons in that N-type semiconductor, the shorter is going to be, the smaller is going to be the time constant. Yeah, extra holes are going to disappear much faster. This will can deduce from this, right? Well, other phenomenon which is very important in semiconductors is diffusion. Yeah, the carriers can be transported in semiconductors through diffusion, something which does not happen in metals. Why doesn't it happen in metals? Because in metals the density of carriers is very huge, and we cannot produce an imbalance in the density of carriers, because the fields are terribly high, and immediately they are evenly distributed, and you have an extra number of charges that go to the surface. You know that from first courses in electricity. Okay, the first fixed law for diffusion states that the flux of whatever we have is proportional to the gradient in the density of what diffuses. The gradient is a derivative, essentially. So in the case of an electrical current, or density of current, yeah, the diffusion, the current diffusion, is going to be proportional to the gradient, which is the derivative of the density. The time constant is d, and this would give us the flux of particles. Yeah, if particles have one charge, okay, that's the reason we have the charge here, then we are going to have the density, yeah, current density. So by including diffusion, then the total current in a semiconductor is the sum of two terms. One is related to what is called the drift, the typical current, because we apply a field with something we saw before. We have the charge, the mobility, the density, and the field, and we have the density diffusion term. Yeah, that will be for electrons, and for holes will be the same, something similar. Be careful with this sign. They are different because these charges are negative. Electrons transport negative charge, so the convention is to define the current as positive, yeah? Positive way, that if the carriers were positive. Oh, here this is the comment I made at the beginning. In metals, diffusion carriers are not important because the electrostatic repulsion prevents significant carrier gradients. In semiconductors, we can have easily diffusion of minority carriers. Which are minority carriers? We will not talk about that. Minority carriers are the carriers having a lower concentration. If we have an N-type semiconductor, minority carriers are holes. And if we have a sea of negative carriers, and we have just a few holes, yeah, the field created by the hole is somehow screened by the negative charge due to electrons. In that way, holes don't see each other. Okay? If that is the case, then they don't repel each other. Then we can have different gradients, we can have a gradient, yeah, of minority carriers. And in that case, the dominant current can be a diffusion current. Yeah? That's the reason. Well, dependence on conductivity and temperature. In general, we have seen that the conductivity in a semiconductor depends on the density of electrons and holes, yeah, and the mobilities. And the conductivity, yeah, in general depends on the mobility and the carrier density. In a metal, the density of carriers, yeah, is practically constant. Yeah, it's exactly constant, the density of carriers. But in principle, the number of carriers have to be the same, are the valence electrons. So the density is practically the same. Why is it practically the same and not the same? Because with temperature, the metal can expand. That's tricky. It was a tricky question. Yeah. So practically, the density of carriers is the same. So in a metal, the conductivity essentially depends on the mobility. Yeah, that's what we said, that with temperature, the conductivity decreases in a metal because the mobility decreases, because the mean free path is smaller. Well, we have two types of dispersion process that reduces the conductivity in general. And each process presents a different dependence on temperature. Yeah, the mobility in the semiconductor, essentially we have two main sources that affect the conductivity as a function of temperature, which are the density, that is a change in the density of carriers, which in intrinsic semiconductors is dominant. Yeah, so the conductivity changes a lot because the number of the density of carriers changes a lot, and the mobility, which is the other factor we have to take into account, has two terms essentially. One term is related to the temperature itself, because we have more phonons. Having more phonons are going to make that the mean free path of carriers is going to be smaller. But at the same time, as we increase the temperature, the role of imperfections in the crystal is reduced. So the higher the temperature, the higher the speed of the carriers. And if there is an imperfection, the higher the speed, the less is the inconvenience that defect creates to a carrier moving. Thinking in a simple idea, maybe, well, I don't know, when I was a kid, I'm talking about things when I was a kid. We used to play with a small, I don't know in English how it is, the smaller spheres, and we played trying to knock the other guy's smaller sphere. Marbles, thank you. Marbles. We used to play marbles. Well, if you and there was a game. At first, you have to put your marble in a small hole you make in the floor. Yeah. If you send the marble just with low speed and you reach that hole, easily the ball, goes into the hole. But if the speed is very high, the marble does not see the hole. Yeah, this is something similar. If the speed of the electron is too high, it does not pay much attention to an imperfection in the crystal. So what I'm saying with this is, on one side, as you increase the temperature, the mean free path of the electrons is reduced because of the presence of phonons. But since the average speed of electrons is larger, the electrons care less about imperfections in the structure. That's why essentially the mobility has a minimum. At the beginning is reduced and then increases because of phonons. Okay, I think I'm going to finish today with this topic, which is really confusing to many, especially to chemists. Again, I'm many chemists around. Okay. What is the work function? Yeah, and we're going to see the junction between two metals. Yeah, but I want to define first what the work function is. So, see this definition, because most chemists I know, at least in my country, define the work function in a different way. The work function is the minimum energy required to extract an electron from a solid. Yeah? Let's think in a metal for a moment. But what do we mean by extract an electron from a solid, from a metal? To take it out from the solid to a point immediately outside the solid surface. immediately outside the solid surface. That's the key point. I've read many times and I have arguments with many researchers because they say to take the electron to infinity. It is not to infinity. It's very close to the solid. Yeah? Immediately there, from macroscopic point, very close. Microscopically, yeah, far away, so we don't have interactions with it. We are far away from the potentials created by the atoms of the solid, but macroscopically close, yeah, immediately there. Yeah. Here we have a sketch of what the work function is. We have the Fermi level in the metal, and this is called the vacuum level. And the vacuum level is the level which is macroscopically close but atomically far from the surface. Yeah? That is called the vacuum level. Well, if we have two separated metals, yeah? I call one metal sample and the other tip because this tip is part of an instrument. I will tell you later what it is, but essentially there are two metals, and two metals having a different work function. Yeah? And here are both metals all separated, and both metals are neutral. That is, they don't have a net charge, those pieces of metal. That's another question for I met with my students many times just to disturb them. How do you make it a piece of metal is not charged? You have a piece of metal and say, maybe this piece of metal has some charge in it. How do you make them to neutralize it? You have no charge in it. Well, 99% of my students say, oh, I'll take a cable and put to ground. I can tell you, 99% of my students say that. Over there. And is that correct or not? If I'm saying that, you have to say that it must not be correct because what is this guy saying? In fact, that is not correct. If you put to ground a piece of metal, what you are making is that the metal is at zero potential, but this is at the potential of the ground, which was supposed to be zero. Yeah? But it's uncharged or charged? Answer, I don't know. Tell me what is around. Maybe that piece of metal, I have another piece of metal above this, which are charged to a potential. So maybe it's a plate of a capacitor, which is grounded, but I have another plate here, and suppose this plate has a potential. Automatically this is charged, and the other one, which is grounded, is also charged with the opposite sign, but it's also charged. In fact, this is the way our old people used to have a piece of whatever charge. To put close something which was charged, it was grounded, and then cut the connection to ground, and then put away the other plate of the capacitor would be, and then we'll be finished with a charged piece of metal. Well, what I'm saying, this is an abstraction because it's very difficult. How can you make a piece of metal uncharged? It's not an easy task to do experimentally. But of course, I can do whatever I want here. Yeah. So let's assume that we have two pieces of metal with different work functions, and both are uncharged. If both are uncharged, there is no field outside that piece of metal. If the piece of metal is charged, we're going to generate a field outside. But if charge is zero, no field. So this is the equation. The vacuum level is the same in both. Because if there is no charge and there is no charge, we have no field between those two pieces of metals. But if we connect both, we can put to ground if you like it, what is going to happen? Well, if the Fermi level is higher than here, now electrons are going to, this is our communicant bases, you say? And they are communicating. The level of the water is the same in both places. Well, here is the same. Charges are going to here from there up to the point where the Fermi levels are the same. And if that happens, that means that we have a negative charge in this metal and positive charge in this other piece of metal. And if that is the case, then the vacuum level here, we have charge here and charge positive, negative here, positive here. We have here a contact potential. It's called contact potential. We have a different potential here. Yeah, we have charge here and here. It's like a capacitor of playing plates. Yeah. Okay. And how can we measure this? Because if we can measure that contact potential and we know the work function of all the metals, we can know the work function for any metal we put on the other side. That's what I call tip. The tip is supposed to be a piece of metal whose work function is known. Well, this is very smart, very clever solution to this. It's called the Kelvin probe method. Do you know of this method? Yeah, Professor knows. Students? Well, the fact is the following. Let's suppose I can make vibrate those pieces of metal. Yeah? Since the difference in potential has to be the same, yeah? If I change the distance, the amount of charge in the plates has to be different to keep the difference here. So if I make it vibrate, you are going to have a current going, yeah, from one direction to the other one. Okay, if you put in between something to measure here the current, we are going to measure a current, yeah, and that is going to tell me that the work function of those pieces of metal are different. Well, how can I make that current is zero? Well, let's add the voltage here to the point in which we compensate this contact potential, this difference, and we make the vacuum levels equal the same. In that case, if I make the vibration, no current, we don't have any current. We have nothing to compensate. Yeah. So if we are adjusting this voltage, yeah, which is power supply, the voltage I have control experimentally, yeah, this voltage is going to be exactly the difference in the work functions of the two metals. Yeah, I think it's very clever. So we need here also an amperimeter, yeah, to measure, to look for this zero current. Yeah, this is called the Kelvin probe method. Okay. Well, I think I'm done for today. We gave you a lot of general ideas, topics. I don't know, I hope this clarify ideas. Hope so. I came here to do that. Or confuse you. Many times confusing is good because it means that you're not understanding something. And it's good to know that one is confused. I'm telling you, the first time I saw these things, they were confusing to me. So surfaces, as I said, are not simple, are difficult to understand. Well, okay, let's stop for today.
So in today's tutorial session, we will look at some of the concepts related to what Professor Celso was discussing. I'll mostly only focus on the intrinsic semiconductors and the extrinsic semiconductors part. He will also do Schottky junctions. The original plan was maybe we'll try and get it done today, but I think tomorrow he will start with Schottky junctions. So that part I will not cover in today's tutorial. So I will try to take some problems and maybe try to make a better connect or a connect to what Professor Celso was discussing this morning. And of course, the session is also open for questions. So anything you guys want to ask, we can stop in the middle and ask me. This will not be such a formal session as what we had now, or a formal session, let's say a classroom. So let's start with an intrinsic semiconductor, and I actually picked gallium antimonide because we are so used to talking about silicon and germanium and gallium arsenide. We just thought it will be a different semiconductor. So we have intrinsic gallium antimonide. So intrinsic again means it's a perfect crystal, there are no defects, no impurities. The question also gives you the effective density of states, so NC and NV, and we want to know what is the carrier concentration. Because this is an intrinsic semiconductor, this is nothing but the intrinsic carrier concentration. So we want to calculate the intrinsic carrier concentration at 300 Kelvin, so at room temperature. And given the electron and hole mobilities, we also want to know what is the conductivity of this semiconductor at room temperature, right? So it's a very straightforward problem and something that you will encounter a lot when dealing with semiconductors. So just to do this, so I'll just open a new screen. This is the formula that we would be using. Ni, which is the intrinsic carrier concentration, is square root of NC/NV exponential minus Eg by 2 kT. Now because this is an intrinsic semiconductor, concentration of electrons is the same as the concentration of holes, so N is equal to P is equal to Ni, right? So I think that's what Professor Celso was also saying, that any electron that is there in the conduction band is coming from the valence band, and the moment an electron jumps, we say that there is a hole in the valence band. So it's just now a substitution of all the values. Eg was 0.67 electron volts, and then you just calculate Ni. So you can substitute all the values. I already did the math, so I have a number. This is around 8.9 times 10 power 13 centimeter cube, right? So this is the number of electrons and holes in gallium antimonide at room temperature. Okay, so far so good. If you see in this particular formula, two things I wanted to highlight. One is the carrier concentration depends exponentially on the band gap of the material. So if I had silicon with Eg is 1.1 eV, so I have a larger band gap. Do you think Ni would be smaller or larger? So if I take a material with a larger band gap, would Ni be larger or smaller? Smaller, right? So because it has an exponential dependence. So if I have silicon, you can do the math. Ni is approximately 10 power 10 per centimeter cube, right? So it is lower than that of gallium antimonide. Germanium has a similar value at around 0.67, so germanium would be closer. If I go even higher, I don't remember the exact numbers. The 10 power 7 for gallium arsenide, do you remember the value? Oh yeah, sorry. So let me erase that. So Eg is 1.43. So it's around 10 power 7, right, for gallium. Yeah, I don't remember the number. So that's why I put this approximate sign. So larger the band gap, essentially lower the value of Ni is. And this has some implications for us. I think tomorrow we will talk about metal oxide semiconductors. They all have band gaps that are pretty large. So if I have something like zinc oxide, band gap is 3.4. If I had some other oxides, typically band gaps can be 2, 3 eV. If I have a large band gap, then this value of Ni is going to be even smaller. and then we will say there is no conduction because there are no charge carriers. But it turns out the moment you have defects in a material, you have polycrystalline material, you have defects, you have impurities, all of those will contribute to conduction. So that's why, especially dealing with metal oxides, we are so interested in the real crystal, which is the defects in the crystal, because they can affect the electrical properties. So let's just go back to this problem. So we have Ni, and now we want to calculate sigma. So sigma is nothing but Ni times E, mu E plus mu H. Again, if I remember right, mu E was 5000 and mu H was 1000, right? So you can go back and check. So mu E, which is the electron mobility, is 5000, and mu H, which is the hole mobility, is 1000. So now all I have to do is to plug in all the values, and that gives me a rho of 11.7. Oh, sorry, just a minute. That gives me a sigma of 0.08 ohm inverse centimeter inverse. So again, it is just doing the math. You get some conductivity value. So let us again try to put this into perspective. If this is sigma, how do I calculate the resistivity? What is rho? So rho is just 1 over sigma, right? Just the inverse of the resistivity. So that gives me a rho of 11.7 ohm centimeter. It's just the inverse. So can someone convert ohm centimeters to ohm meters for me? So what do we do? Just a unit conversion, right? So let's put it in ohm meters. So you have to divide by 100. So this is 0.117 ohm meters. So this is the resistivity of gallium antimonide at 300 Kelvin. So in yesterday's tutorial, we looked at gold. I think we saw metal. Does anyone remember what the resistivity of gold was? This was from yesterday's tutorial. (24 nano ohm meter), right? So somewhere around 24 nano ohm meter. Resistance was R, that is ohms. So resistivity would have been ohm meter. So 24 nano ohms is 2.4 10 power minus 8 ohm meters. And this actually allows us to compare. So gold is a metal, it's a very good conductor. Gallium antimonide is a semiconductor, it is not so good, and you can see that there is nearly 7 orders of magnitude difference in terms of conductivity. If instead of gallium antimonide I had an insulator with a much wider band gap, you would have obviously a much lower or a much higher resistivity, much lower conductivity, and again the difference will be orders of magnitude. So all of this is related to the fact that gold does not have a band gap. You have one band, which is your valence and conduction band, so it's very easy for charge carriers to move, while a semiconductor has a band gap, which means the electrons have to jump from the valence band to the conduction band. So how we do that is essentially the reason why you have this wide difference. Just to sort of finish this particular question out, so again let's go to gallium antimonide. what happens to sigma as temperature increases, right? So what is going to happen to the conductivity or the resistivity, but we'll just stick with conductivity. What's going to happen to sigma as temperature increases? So you go back to the equation Ni. First we will look at Ni. So maybe instead of sigma I will first say Ni, and then we will talk about sigma. So Ni is square root of Nc Nv exponential minus Eg by 2 kt. Nc is 2 pi me star kt by h square. I will write the equation slightly different from how Professor Celso would write. You would use h or h bar? Both, right? So physicists use h bar a lot. Everyone else uses h. So we will just use this is the formula I would remember off the top of my head. 2 pi mh star kt. So both of these have a temperature dependence. So both Nc and Nv also change with temperature. Typically when I increase temperature, what's going to happen to Nc and Nv? They will also increase, right? Because you have a temperature term here. This exponential term, the temperature is in the denominator and it's also negative. So again, as temperature increases, this term will also increase. It turns out the exponential is much more stronger than Nc and Nv. The change with temperature is much more stronger. So if you were to make a plot of ln of Ni versus 1 over T, you would get more or less a straight line. If you don't believe me, you can always go and plot it. It's very easy for you to plot it in Origin or MATLAB, Excel, and the slope of this is just minus Eg by 2k. So when Professor Celso talked earlier, he talked about semiconductors having a higher conductivity as temperature increases, and that is because your carrier concentration also increases. Just to again round it out, so we have sigma is Nie mu E plus mu H. As temperature increases, Ni increases, but typically in almost all materials, as temperature increases, mu E and mu H decreases. Celso, would this be a general rule or would there be exceptions to this rule? Exactly, right? So we will always say that whenever the temperature increases, mobility decreases. So mobility is nothing but how easily the electrons or holes can flow. As temperature increases, you have more lattice vibrations, more phonons, which means it's easier for the electrons and holes to scatter. So the mobility actually drops. So now we have two things. So I have one term which increases as temperature increases. I have two terms which actually decrease as temperature increases. But again, Ni is the term that dominates. So overall, sigma increases as temperature increases. So this is the biggest difference again between metals and semiconductors. In both cases, the mobility reduces. In the case of metals, the charge carriers are already large, they are not going to change with temperature. But for semiconductors, as temperature increases, the charge carrier concentration will also increase, and that is why the overall conductivity is higher. Okay, any questions?
So
Yeah.
sir, if we can
compare polycrystalline material and single crystalline. So how will be mobility means it will decrease with increasing temperature. Okay, so let us take polycrystalline and single crystalline both at the same temperature, right? Polycrystalline will have lower mobility than single crystal because polycrystal will also have grains. So grains will additional scattering points. So its mobility anyway will be lower. And when you increase temperature, both will have similar phenomena, right? So single crystal there will be more phonons. Polycrystalline you will have phonons, you will have grains. Let us say you create some other defects like vacancies, they will further affect the mobility. So both cases with temperature the mobility will be lower. Is correct?
It's correct. In polycrystal, you have to sum up the intergranular values. Makes things more complicated.
Yeah. So when you talk about
Of that, like,
yeah. So he will talk about that later. Yes. Okay. Any other questions? Yeah.
So what happens to law of mass action as the temperature increases? So
What happens to the law of mass action? So are we still talking about intrinsic or okay, it doesn't matter, right? So law of mass action just says Np equal to Ni square. This is true at all temperatures. So if I have an intrinsic semiconductor, Ni goes up, correspondingly N and P also go up. If you have an extrinsic semiconductor, which is what we will talk about later, the same will be valid. What happens when we have an extrinsic in the intrinsic regime, right? It would still be valid.
An extrinsic, essentially, if you have an n-type semiconductor, n is not going to change much.
Yes.
P is the value is going to change.
So either way, this rule is valid at all temperatures. Any other questions? Alright, so moving from intrinsic, we will look at an extrinsic semiconductor example. So we'll go back to silicon. So now we have again a silicon wafer. We will still take this to be an ideal wafers or ideal crystal, so single crystal, no defects. In this I am adding around 10 power 15 antimony atoms per centimeter cube, right? So antimony, anyone know what group it is? It's N type. What group on the periodic table? Pentavalent, right? Sorry. So group 5, right? So they are pentavalent group 5. So now we want to know what the electron and hole concentrations are, and this is an information that we would have. So let's go here. I don't want to waste the space, so we'll do this. So I have silicon at room temperature, so 300 Kelvin. Let us assume that initially my silicon is intrinsic. I don't have any dopants. So N is equal to P is equal to Ni. This is equal to 10 power 10 per centimeter cube. Right? Now I'm adding 10 power 15 antimony atoms per centimeter cube. So you already told me that antimony is pentavalent, so it's 5 electrons. So each antimony atom is going to donate 1 electron, right? So you would basically have 10 power 15 electrons from antimony. So just to find out what the concentration of electrons is, we write what is called a charge balance equation. Again, Professor Celso wrote that, which says N is equal to Nd plus P. All this says is this is all the negative charge, this is all the positive charge. So the total negative charge and the total positive charge must balance. So I will just take a new page. So we have the law of mass action, Np equal to Ni square. Remember, Ni is 10 power 10. N is equal to Nd plus P. N is equal to, Nd is 10 power 15. This is the number of antimony atoms that we have added, each of which gives 1 electron, plus P, which is Ni square over N. So this is actually a quadratic equation that we can solve. You have N here, you have N here. I can show you the math, but remember Ni is very small, right? So Ni is only 10 power 10. This is 10 power 15. If you actually do the simplification, you will get N to be 10 power 15. P would be 10 power 10 square by 10 power 15. So this would be 10 power 5 per centimeter cube. So again you would have an n-type semiconductor with around 10 power 15 electrons and 10 power 5 holes. So this makes it an n-type semiconductor. Then we make things a bit more complicated. To the same sample, you are now going to add boron atoms, and again there is a particular concentration. So if antimony is pentavalent, what's boron? Trivalent, right? So boron is group 3, it's the other side of the periodic table. So now you add boron atoms, so of around 10 power 16 centimeter cube. So boron is trivalent, so these are called acceptors. Antimony is donors, so Na is 10 power 16 centimeter cube. I already have Nd, which is 10 power 15 per centimeter cube. So I have both donors and acceptors in my material. I can now write the charge balance equation. So N plus Na is P plus Nd. So all the negative charges on one side and all the positive charges on the other side. So N plus 10 power 16 is equal to P plus 10 power 15. There is more boron than antimony, so I can write this as N plus 9 times 10 power 15 is equal to P. Because there is more boron than antimony, the net effect is that this is a p-type semiconductor. So I can write this as Ni square by P. And again we can solve this as a quadratic equation, but this term is usually very small. So now you get P equals to 9 times 10 power 15 per centimeter cube, and N is 1.1 times 10 power 4 per centimeter cube. So you started off with an n-type semiconductor. To that you added enough borons so that you actually changed the nature of the semiconductor from n-type to p-type. This is called compensation doping. This is something that people use when they are actually making semiconductor devices. They want to make junctions. They go for this sort of an approach. Any questions? Did we talk about Fermi level in extrinsic? Did you talk about it? Okay. So yeah.
So while doping silicon and germanium with third group or fifth group elements, so it always goes and sits in the substitutional position, or there is a chance that it will go to like interstitial position in between silicons.
Okay, so what determines whether a particular atom goes into interstitial or substitution? I'm asking you.
That the energy we are implanting,
Forget the energy, there's something much more basic,
the
right?
size ratio of atomic.
The atomic size ratio. So basically you go back to your Hume-Rothschild rules. So the size is basically what determines. So if I have silicon, I don't know what's the void size in silicon, I don't remember. But your dopants are such that they would not go into the voids. They would always be substitutionally doped. You can calculate the energies as well to say, okay, if I have silicon and I try to put boron or phosphorus, what would be the energy? But I think you'll find that it's negative. So it's the size that of the dopants that affects that. Yeah.
Just going to interstitial position, there is no usage of carrier concentration increase, no bonding.
If it goes to interstitial, what happens? It will not go.
Now, where we want to go.
Yeah.
So there. Now, typically, the temperature is heated up, so the guys can diffuse. They diffuse into the silicon, and they look for a lower energy position, and then it becomes a diffusion. It comes naturally because energy is pushing in that direction. That's the manner in which the silicon wafer is built. They put the masks and they send those impurities, heat up, and it diffused into the silicon. And they go to that position because that's the energetically equivalent position.
Okay. So again, maybe just to round up, I think Celso talked about it, but I will also just talk about the Fermi level position just to round this up. So let's go back to silicon. I now have three diagrams. I have intrinsic, N-type, and P-type. So this is my valence band, this is EV, and then this is conduction band, EC. I'm just marking just at both the ends. We'll also define a vacuum level just so that we can also talk about work function. So this is my vacuum level right at the top. So if I have an intrinsic semiconductor, I will also make life easy for me. I will just say NC is equal to NV, right? So this is again the symmetric situation that Prof. Celso talked about, where the number of effective density of states, the valence and the conduction band edges are the same. So if NC is equal to NV, in an intrinsic semiconductor, EFI, the Fermi level, is going to be right in the middle. So it's going to be the band gap divided by 2. So it's going to be right there. From the Fermi level to the vacuum level would be the work function, right? So phi I. If I have an N-type semiconductor, so same semiconductor, we'll just take silicon as an example. Even though silicon NC is not equal to NV, you can just use silicon as an example. So now I have an N-type semiconductor or N-type silicon. So I have added some donors so that I have created more electrons than holes. The Fermi level shifts up. That's what Professor Celso had also mentioned. This Fermi level shifts up so that it is closer to the conduction band of the material. So this is EFN. Now I can again define a work function. that is phi n. Now instead of n type, I have p type. My Fermi level will now shift down because I have more holes than electrons. So that's EFP, and I have a new work function phi p. So it's the same material, it is silicon in all three cases. One is intrinsic, one is n type, one is p type, and then you can clearly see that phi n is less than phi I is less than phi p. So essentially the work function will change depending upon the nature and the type of the dopants that you would have in your particular semiconductor. And I thought that's again something that you should be aware of. This concept of changing work function is what people make use of in junctions. So if I want to have a PN junction or a metal semiconductor junction, whether it's Schottky or ohmic, the difference in the work functions that leads to a contact potential. Professor Celso talked about it towards the end. That contact potential arises because we have a difference in the work functions. Okay. Any questions? So we make two assumptions here in all of the discussions that we had today. One, of course, is you have a semiconductor that has absolutely no defects. Turns out once you have defects, which is what most real semiconductors do, and that's what we will spend the rest of the course talking about, many of these will change, many of these behaviors will change. The other assumption is, of course, whenever I have donors and acceptors, we assume that they are 100% ionized, which means if I have 10 donor atoms, all 10 will donate 1 electron to the conduction band. This is true at room temperature for semiconductors like say silicon, germanium and so on, but not necessarily true always. So again, when you're dealing with real semiconductors, say you're doping it, it's possible that your dopants are not completely ionized, in which case that will also affect the charge concentration. But as I said, those are topics that we will discuss in the next couple of days. Again, this is just to establish the basic framework for you so we can build upon it. Anything you want to add? It's fine. Okay. Yeah.
What is this doping of either boron, silicon, or antimony or
Phosphorus, yeah.
can never be interstitial.
Yes. It will always be substitutional, that's correct.
So, the elements like boron, carbon, oxygen, nitrogen, and hydrogen can only sit in interstitial.
So, but why are we talking about carbon, oxygen, nitrogen?
Because when I studied about Hume rules,
Okay.
I studied that only these 5 elements can sit in interstitial. Other than this, nothing can sit in interstitial.
But okay, let's go back to Hume-Rothery rules. They were more for metals, right? So whether we could use Hume-Rothery rules as such for silicon, I would not know. So for boron, we know boron in silicon is substitutional. If I had oxygen, oxygen would not diffuse, right? Oxygen would rather react with silicon because most of the doping is essentially a high temperature process. So you expose your wafer to your dopants at high temperature and then they diffuse. So if I have silicon, I heat it to high temperature and I expose it to oxygen, I will not have oxygen diffusing into silicon. Rather, I would have silicon reacting with oxygen to give me SiO2. If I have nitrogen, I would have silicon reacting with nitrogen to give me nitride, silicon nitride. Carbon, I'm not so sure what carbon would do. I know there's silicon carbide, but I don't know whether that's how you would actually make silicon carbide. Is there, but is that how you make react carbon with silicon? It might be a bit more complicated than that, but that's the point. So if they form compounds, if the compound has a lower energy, that will form, it will not dope. But boron is substitutional, it's not interstitial.
Silicon carbide is there, but
So that's just I think some like with the combination is there.
yeah.
So for the nanomaterials, they are using the SiC.
But again, I don't know how you synthesize SiC. What is the synthesis procedure? Even nitrogen, you will not expose nitrogen gas. You will mostly either use some other gas, so either ammonia or something else. So you can break down nitrogen. If I want to form silicon nitride, right? You will not mix silicon with N2 gas. N2 has a very stable bond. It's very hard to break N2. So you would use some other gas like ammonia. So that gives nitrogen that reacts with silicon, and that gives you silicon nitride. Okay. Any other questions?
Sir, after doping, how to ensure how much depth doping happens, like depth profiling?
So one is you can control the time and temperature. You can also measure the dopant depth. There is a technique called secondary ion mass spectroscopy (SIMS). So SIMS can be used for you to do depth profiling.
That's a tech.
Standard rules are there, sir. Micron rules, lambda rules are there, sir. Based on this only we can fix the diffusion.
Yeah. So you again, depending on whether it's a gaseous source or a solid source, you have those formulas that tell you what is concentration as a function of depth for some time and temperature.
So to confirm experimentally, we have to go for SIMS.
SIMS is what people normally use. Yeah. Any other technique that you are aware of, Celso? No, right? APT, no. APT will not necessarily work for this because I'm not. I think APT is too advanced for this. That's because APT tries to reconstruct, right? It is not just concentration. APT also tells you where the atoms are. At this low ppm, APT will not work. SIMS is probably the best.
So then what about doing XPS and polishing? XPS polishing, will it work?
You can also do depth profiling with XPS, you are correct. But again, your dopant concentration is parts per million. At that low concentration, you may not be able to detect the signal. So that's the problem with XPS. So that's why people use SIMS, because SIMS basically secondary ion, right? So you use argon for SIMS. Yeah, so you use argon ions which then bombard out, and that has a much better resolution. Yeah. Okay. Well, there are no further questions, then we will stop the session today. So hopefully I'll see you guys in the afternoon at 3 o'clock for the talk. If not, we'll anyway meet here tomorrow in the morning for the class. Alright, so see you guys. Thank you.